turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists podcast, the programme that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith, and today, the scientist who used a brain scanner to talk to a patient in a persistent vegetative state to reveal she was still in there. We're journeying to the centre of the brain, and our guide is neuroscientific titan Adrian Owen. Neuroscientist and best-selling author Adrian Owen was born on the 17th of May 1966 in Gravesend, Kent. He went to Gravesend Grammar School and later studied psychology at University College London. After earning a PhD in neuropsychology from the Institute of Psychiatry in 1992, followed by a spell in Canada at McGill University, Adrian returned to the UK in 1997 to join the Medical Research Council's Cognition and Brain Sciences unit in Cambridge, where he ultimately became the assistant director. In 2011, he moved to the University of Western Ontario, where he's now Professor of Cognitive Neuroscience and Imaging. In 2024, he was made a Fellow of the Royal Society. During his career, Adrian has made breakthroughs in solving how different parts of the brain contribute to cognition, memory and consciousness, and he pioneered the use of touch screen technologies used globally to test cognitive function and identify early signs of degenerative diseases and probe conditions like OCD, autism and ADHD. But it was in 2006 that he published the paper in the journal Science that really catapulted him to international science stardom, documenting as he did how, with the use of a brain scanner, he'd been able to communicate with a patient in a long-term vegetative state after a brain injury sustained in a road traffic accident. Adrian, it's almost 20 years to the day since that paper first came out and we first met when you joined us on the programme to talk about your work. It is lovely to welcome you back on such a significant anniversary.
well, thanks for having me.
Can we start really at the beginning, at the basic side of this, which is we refer to this thing called a brain, but actually most people have never seen one. What actually is a brain?
Well, the brain is really just an extremely complex combination of neurons and neurotransmitters and cells, and and I think the problem with trying to ask the question, what is a brain, is that you can think about it at a number of different levels. Rather like a forest, you can think about it as being a bunch of trees, or you can think about it as being tens of thousands of leaves. Same thing with the brain. You can think about it in big general areas. There's the big lobes, and then you go down even further into the sort of cells or the neurochemistry. It starts to get immensely complicated. I'm a cognitive neuroscientist, so I'm somebody who wants to understand how the brain works. So I tend to take a functional approach to describing it. If somebody, as you just did, says, well, tell me about the brain, I would say, well, the bit at the front is that does all the heavy lifting thinking, the decision making, the planning, the problem solving. The bit at the back does vision. That basically decodes information coming from the outside world through the visual system to help you see. The bits on the side do hearing, so on and so forth. So I tend to think of the brain in functional terms as which bits do what.
How do people know that what you just said is true? As in, this bit on the side here helps me hear or decode speech. This bit at the back is used when I'm looking at you now, for example. How do we know that? And when did we first begin to grasp that that was how the brain is organised?
The idea is basically that if you lose part of your brain because maybe you have a tumour removed, or you've had a traumatic brain injury, or had a stroke that's damaged that part of the brain, and we look at what you can no longer do, we can work out what that missing part of the brain was responsible for. That's the basis of neuropsychology, and it really became a sort of systematic science in the 50s and 60s. That was how we understood how the brain worked. Now, of course, at the end of the 80s and the beginning of the early 90s, we saw the arrival of fantastic neuroimaging techniques like PET or positron emission tomography, and later fMRI, functional magnetic resonance imaging. The advantage here is that you don't have to wait around for a patient to come along with a particular type of brain damage. You can put a healthy participant into the scanner. You can have them do the thing you're interested in. Hey, think about a complex math problem and look at which parts of the brain are activated when the person does this. And again, you're making that connection and saying, okay, if that bit of the brain lights up when that person is doing that thing, that part of the brain must at least be involved in that thing. So it's really changed very much in the last 30 years how we do this. And in many ways, neuropsychology is still a very valuable discipline, but functional imaging has pushed us much further in recent years.
And this whole question of you only use 10% of your brain at the time, where did that come from? And is there any grain of truth in that, or is that completely wrong?
I think, again, it goes back to your level of description of the brain. So, if for example, I ask you to remember a series of digits, Chris, then various bits of your brain are going to be involved in that. They're going to help you do it. They're going to light up in an fMRI scanner. But I doubt more than about 10% of your brain is going to respond in that way. So I guess in some sort of functional sense, saying you only use 10% of your brain, if you interpret it as in each thing you're doing might only involve about 10% of your brain, I think there's probably some truth in it. I think it's got a little bit twisted, and certainly the generalization of the idea that you only use 10% of your brain doesn't have any basis in truth at all.
Although there are possibly some people on Earth where that is the case. I can think of a few I've come across.
Well, yeah, it's interesting. I mean, there's certainly people use their brains in different ways. And it's certainly true that people, particularly where things like the frontal lobe are concerned, where these are the areas of the brain that are responsible for so-called executive functions, for decision-making, planning, problem-solving, reasoning. Certainly, some people use those areas of the brain more than others, and they apply them to particularly problematic situations like solving complex problems.
Now, is that because, and if we take, say, the cryptic crossword as an example, there are some people who are really very good at that, and other people who they're just bamboozled and they just can't think along the right lines. Now, is that because some people have a particularly well-developed bit of the brain that's good at doing that particular thing? Or is it that they've practiced? Or is it that different bits of the brain that deal with that task are very good at talking to each other, so they can pass messages backwards and forwards and break the problem apart in the right way, so it can be tackled?
All of those things can be true, Chris, in different situations. It depends what it is you're trying to achieve. So, for example, we had a study recently where we looked at people that play a lot of video games. And what we found is that they had higher performance on many of our cognitive tests. But really, it was the type of video game made a big difference. You had to be playing something that involved decision making, working through a series of problems, working through an environment, these sort of very high resolution sort of modern games, as opposed to the sorts of things I grew up with, like Space Invaders and Asteroids, where you're just mindlessly shooting at spaceships. And that really is probably an effect of the enormous amount of practice and brain plasticity, if you like, that's gone into the time spent playing those games that often involve a lot of very difficult hand-eye coordination and so on and so forth. And it certainly improves performance on some cognitive tests. But again, it's not true of everything. Certainly, there are many, many video games that don't improve your performance on any cognitive tests. And I think it has to do with which parts of the brain particular games recruit, how much practice you do. All the things you have already suggested, I think, will play different roles depending on the specific game and the specific type of activity.
Does it generalise, though? So if I spend every day doing the cryptic crossword and I do become better, does that generalise so that I will automatically improve my musical capabilities, my linguistic capabilities, or do I just become very good at the task I'm practicing at?
Yeah, so when was it? 2010, we published a paper in Nature, which I think is still the largest brain training study that's ever been conducted. We took 11,400 individuals and we had them play a so-called brain training video game for 6 weeks, several hours a day for 6 weeks. So it was a big study, lots and lots of training. And the amazing thing is that the people got really good at the games. I mean, 6 weeks of practice, but there was no generalized ability at all. For me, the part of that paper that has really stood the test of time is that we looked at tests that were very similar to the train tests, and even ones that were really similar. Like, instead of remembering a series of numbers, you would remember a series of blocks on the screen. You're still remembering stuff. It's still a relatively small amount of information. There's a lot of overlap between the tests, but remembering numbers didn't help you remember boxes on a screen. Remembering letters didn't even necessarily help you remember numbers. So I think this is one of the really interesting things about brain training, that if you practice something, you are going to get a lot better at that thing. But at least I would argue you don't get better at anything else.
Do we understand, given that we have this compartmentalized view of the nervous system, that the bit at the front is where I'm making decisions, the bit further back is where I'm making movements, the bit behind that's where I'm feeling what's going on, and the bit behind that's where I'm seeing what's going on, and the bit round the side is helping me recognise your face, for example. Beyond that, do we understand how all those different bits actually talk to each other? Because in isolation, you've just got a bunch of functions distributed across this grey matter, but how do they actually coordinate what I'm thinking, so that I look at your face and I say, that's Adrian Owen, and he knows about neuroscience and consciousness and so on. How does it all come together?
Yeah, that's a great question. And I must say, your little map through the brain's anatomy was spot on, by the way. Well done. But of course, it was based on a classic neuropsychological view of the brain. And this, I think, is a really good example of where imaging has provided some really interesting new answers. So that, the problem with the classic approaches of taking a patient who's got brain damage, looking at what it is that they can't do, is it's very much dependent on localization. You only find out what that bit of the brain did, and you really don't find out anything about how it's connected to other parts of the brain and how those connections might have been affected. Because, of course, if you take a piece of your brain out, it's not only that you can't do whatever that piece of brain did, but it's that there are no longer communications with the rest of the brain from that area, and all those connections may have also been contributing various functions. So now we have a number of methods available to us with imaging that are very interesting. I mean, some of them just look at functional connectivity. So you put somebody into a scanner, and because we can scan the whole brain, we're not only looking at the frontal lobe when somebody's thinking, we're able to say, well, yeah, but how is the frontal lobe dictating to the parietal lobe about what it should do or where it should go or what decisions should be made? And so we're learning much more that no brain system or area works on its own. The brain does work as a very integrated unit with many, many millions of connections between neurons. But also structurally, imaging has provided us with lots of information. I mean, historically, it required neuroanatomists to dissect brains and work out what was connected to what. And of course, that's very painstaking and problematic work in many ways. It's hard to do. Nowadays, through imaging, we can map those connections with techniques like diffusion tensor imaging, or DTI, is a method for looking at how multiple brain areas are connected with one another. And from this, we can, in a way, visualize the highways of the brain and work out how all these areas are connecting. And it's throwing up some huge surprises. Sometimes things aren't connected directly, but they're connected indirectly through a sort of a backdoor connection. So again, imaging is contributing a lot in that area.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
You're listening to the Naked Scientist podcast with me, Chris Smith, and today we're exploring the inner workings of the brain, including next how consciousness occurs and how my guest, Adrian Owen, used a brain scanner to open a channel of communication with a patient in a long-term persistent vegetative state. How does consciousness work, though? And is consciousness a kind of construct where all these brain areas do their thing, share their information, exchange information in the way you've been saying, and then something sort of filtered or skimmed off and created into a sort of snapshot, moment by moment, that is me being conscious? And what's the time lag between the brain areas doing their processing? Because that takes time, doesn't it? Nerve cells have got to talk to each other. That's going to take time. So how long does it take between them talking to each other to then distill off what I think of the here and now being?
Right. Well, of course, it's extremely fast. Information travels along neurons, much faster than a final serve at Wimbledon. These are extremely fast speeds. So the information, I mean, you're right, there will be delays, but the information travels very quickly. I mean, consciousness really, I don't just tend to think of it as something that's sort of carved off. I tend to think of it as being the net result of all of this computation. That it is, at the end of the day, the feeling that you end up having, the thought that you end up having, the memory that is elicited by that event. So it's every experience, emotion, movement, feeling that we've ever had. It's a product of that complexity, that it's so complex. There's so much going on. There's so many things communicating really very efficiently and effectively with one another that what emerges from that is a sense of being, and that is consciousness. I am somebody, and I live in the world, and I interact with the world, and the things that I think and do have effects on the world.
So is my dog conscious then? Because if I look at the dog's brain, it's got all the same bits that my brain has. They differ in size and shape and level of development, because obviously a dog lives in a smell world, I live in a visual one. But does that mean my dog probably has consciousness like I do?
Well, it's funny, I just finished a book, but it's ostensibly about executive function, but I ended up talking a lot about our dog, trying to address exactly this question. I think undoubtedly there is a sense in which your dog is conscious. I suspect its consciousness is not the same as yours and mine, and that doesn't mean to say it's less conscious or it's more conscious. It's just conscious in a different way. As you say, a dog has a whole smell world that we don't have. Your conscious experience of the world is very much determined by what you understand about the world. When you see a gun, that may induce a sense of fear in you, because you know that guns, they can be used to kill people or shoot people, and that's because you have a representation of what a gun is for, what it looks like, what it's used for, what it has been used for historically. Well, take a dog, or particularly a young dog, never seen a gun. Right? There's no reason why a dog would be scared of a gun. It's just a piece of metal. I mean, that doesn't make the dog any less conscious of the fact that it's a gun, but it does mean that its conscious experience of seeing somebody holding a gun might be like your conscious experience of seeing somebody holding a piece of metal. And so if you think about that, it becomes obvious that much of our life is dictated about this. The assumptions that we make about the world, the beliefs that we have about the world, the way we experience the world is very much shaped by what we know about the world. The immediate problem with saying, is my dog conscious, is that its world is different to your world.
Where does that leave us then with computer programs? Because I spoke to Nikki Clayton recently. She was one of our previous Titans of Science, talking about her work with corvids and so on. And she'd just come back from a conference internationally where she was joined by Buddhist monks and computer programmers, because they were thinking about the idea that when you create a computer program of sufficient complexity, does it become conscious? Does it fit the definition?
Well, I think, again, it's a really difficult question because things are evolving so quickly. I mean, even 2 or 3 years ago, I don't think any of us we'd have talked about this theoretically, but I don't think we would be asking things like, well, is this LLM conscious or not? Where of course, a lot of people are starting to do that now. And I mean, for me, no. I don't think these machines are conscious, nor do I think they're going to become conscious anytime soon. And I think it has a lot to do with how we think about consciousness, and maybe we need to change the way we sort of define it a little bit, in the sense that I think up until now, a lot of it has been based on our understanding has been based on what is required for something to be conscious. And, often I think we think of, well, if something can solve a complex problem, it must be conscious. And of course, computers can now solve extremely complex problems. So I think the problem is we've tended to mix up intelligence, if you like, or problem solving ability with consciousness. I think machines have shown us that the two things don't have to go hand in hand at all.
The flip side of consciousness is unconsciousness. So what is that?
Well, I tend to think of it as total oblivion because of the sorts of patients that I work with in my lab. For me, unconsciousness is a complete absence of any experience. So somebody who is truly unconscious, and they don't need to be necessarily a patient who's had a brain injury. It could be somebody who's had a general anesthetic. It's total oblivion. You have no sense of who you are, where you are, and the situation that you're in. Anyone listening to this who's had a true general anesthetic, and I don't mean a bit of sedation to have a wisdom teeth removed. The amazing thing is you really are gone from the world. It's not just that you're asleep, because when you're asleep, you have some sense of what's going on around you. The amazing thing about anesthesia is you have no sense about how much time has passed either after a general anesthetic, which I find fascinating. And I think that's because as far as the brain is concerned, time hasn't passed. It's a complete absence of any experience whatsoever.
The reason that you and I first met 20 years ago is because you published a paper which sent shivers down spines internationally, which is that you'd been looking at a group of patients who we regarded as unconscious, fulfilling many of the criteria you just outlined, who we thought had no ability to interact with the world, and you effectively were able to get through to them. How did that come about?
It started about 10 years earlier with us doing things or presenting stimuli to patients who are supposedly in a vegetative state. And that's a condition, it's often described as wakefulness without awareness, because patients open their eyes, they have sort of roving eye movements, but they won't respond in any way. If you ask them to squeeze your hand, they won't do it, or blink an eye, they won't do it. And the assumption was always that these people have no awareness whatsoever. But over the years leading up to the 2006 paper, we'd done things like shown these patients pictures of faces and seen the parts of the brain that we know are involved in processing faces light up. We played speech or little brief stories to some patients and shown the areas of the brain that we know decode language would light up. And this, of course, always led to the question, yeah, but are they conscious? Is the brain just doing this automatically, or are they having some actual conscious experience of what's going on? And that really took us to the 2006 study where, yes, one patient who had been in a road traffic accident had very severe brain damage and had been supposedly vegetative for a number of months. And what we did is we decided to ask her to generate activity without actually a stimulus. So we didn't just show her a face and look for the face area, or some speech and look for the speech area. We said to her, if you can hear us, we want you to think about playing a game of tennis. So it wasn't that we were doing something to her that could elicit an automatic pattern of brain activity. It was that she had to do something to show us that she was in there. And sure enough, what happened when we asked her that is that the area of the brain that we know is involved in complex movements, it activated. And it didn't just happen once. We'd say, well, think about playing tennis, and that area would activate. And then we said, okay, stop now. And activity in that area would immediately dissipate. And then we'd say, okay, think about tennis again. And activity in that area would take off. It was the sort of brain equivalent of asking her to squeeze my hand. And that's how we, in a sense, unlocked her consciousness and showed, in fact, that she was completely aware.
What was that like when you watched that happening in real time? What was your reaction?
Yeah. Well, interestingly enough, in those days, we didn't see it in real time because the scanners weren't sophisticated enough or fast enough. So actually, while she was lying in the scanner, we didn't know that she was conscious. We had to take the data away and analyze it. And that probably took a few hours, maybe a day or so. And, suddenly out pops this brain with an activity in exactly where I'd predicted it was going to be, exactly when I'd predicted it was going to happen. And, my first response was, this can't be true. Let's look again. And we'd look again at a different run because, of course, we replicated this several times. And sure enough, it was replicated over and again. And we had another task. We had her also thinking about walking from room to room in her house. And that was just to make sure that this was generalizable. It wasn't just one thing that she could do. And when you think about walking around a familiar environment, you activate again a pattern of different brain areas, but it's a completely different pattern than the tennis playing pattern of areas, if you like. So she could do that too. And she could switch from one to the other. Do tennis now. Now think about moving through your house. And so honestly, I mean, it was utterly convincing. That was my strongest reaction at the time. Not only was this incredible that we'd managed to do it, the data itself was utterly convincing.
What were the implications of that, ethically, medically, and so on?
Well, I mean, the implications are still unfolding 20 years later. I mean, at the time, there wasn't too much we could do about that particular patient because she was in a long-term vegetative state. We don't have a treatment or a therapy that we know can be used to bring people out of those situations. So there really wasn't very much that we could do. I think ethically, even immediately, that it showed that there is an impetus to get the diagnosis right. I mean, it does change a lot of things. If you go from a situation where you think this person that maybe you once loved is gone and is lost and is living in oblivion and has no sense of who they are and where they are and the situation they're in, to a situation where you suddenly realize, oh, they're aware. They're listening to every conversation that is being had at the bedside. They understand those conversations. If we make a decision about what we're going to do with this patient, they're going to witness that decision. That, does change everything and has obviously ethical implications. We went on to develop the technique to test many, many more patients to show that this actually is true of about 20 to 25% of patients who appear to be completely non-responsive actually are in this situation. So that's one interesting thing. It also has some implications for your likelihood of recovery. And again, that's in terms of how one allocates resources and, keeping people alive and all these sorts of things, withdrawal of life support. It has implications down the line for that because your chances of recovery are somewhat higher if you're in one of these situations than if you are in a truly vegetative state.
What's the difference between someone who is vegetative and someone who's in a coma? Because I know Hollywood has a particular way of doing this where there'll be someone who suddenly coughs and wakes up having been unconscious for a long period of time. Is that completely fabricated, or do people do that? And if so, what is keeping someone in an unresponsive state and means that they then seem to come back in that way?
I think that's a very idealized version of coma and vegetative state, the one you see in movies. I mean, the other point that I try to make in situations like this is that, this is not pretty science. When you see, a movie and the person is lying peacefully, looking basically perfectly normal, as though they were asleep in a hospital bed, I don't think I've ever seen that. I mean, these patients have typically had extremely severe brain injuries. They'll have a lot of equipment attached to them. They'll be being kept alive with life support systems. I mean, it's a very, messy, and some people find it a very unpleasant situation. So the Hollywood version of coma doesn't exist, I don't think. Coma typically occurs before a vegetative state. So coma patients typically have their eyes closed and they don't have sleeping and waking cycles. They sort of look truly unconscious to most of us. They'll just lie mostly motionless. This typically happens in the first few days after a brain injury, and it may last a few weeks, but that would be unusual to go that long. What often happens after that is the patient gradually wakes up. They don't suddenly open their eyes and sit up in bed. Unfortunately, they gradually start to respond and get communicative with the outside world. And they may improve to the point that they can go back to some of their previous activities, or they may enter a long-term vegetative state, and that involves them opening their eyes. A vegetative patient will typically have eyes open, so they are wakeful, but they appear to have no awareness of the outside world. And vegetative state can last for decades. I mean, I've seen patients 25 years on in a vegetative state. People don't really do 25 years in a coma. They'll either emerge, die, or recover.
Has this changed the way that you think about how you would like to be cared for, or what would happen if you were in a position like that? Has it changed your perspective, what you've discovered?
It has. A lot of people say to me, well, you must have an advance directive then. You must have written down what you want to happen to you in that situation. And actually, quite the contrary. It's convinced me that an advance directive is not what I need, because what I think I want to happen to me, should I be unfortunate enough to end up in a coma or a vegetative state, I now know is probably not what I'll want when I get into that situation. And we know this from talking to patients who've recovered. We know this from patients who have been able to communicate while in these situations. And I think while most people will say, I never want to be in that situation, pull the plug if I ever end up in a coma, in reality, we know that's not actually true. When you get in that situation, your opinion may well have changed. And that's where I am. What I want to do, should I ever be unfortunate enough to be a patient in this situation, is I want somebody to get me into an MRI scanner and ask me to imagine playing tennis.
Profound and thought-provoking stuff. Adrian Owen, our titan of science this week. And Adrian's latest book, Think Before You Think, which explores much more of what we've just been discussing, is out from August 2026. So be sure to give that a look. Now, we're back with the latest science news stories from the week on Friday, including documenting the algae bot, how scientists have used algae to build microscopic steerable robots that can deliver drug payloads to precise locations in the body. Tune in for that. Meanwhile, if you appreciate what we do here and you would like to show your support for our work, then do please consider making a donation to help keep the show on the road. You can do that at nakedscientist.com/donate. I'm Chris Smith, thanks for listening, and until next time, goodbye.